All right, ready? Right. What do you think, Chris? What do you think electromagnetism means? Electromagnetism. If you can make a guess. Electro is what? Electricity. Magnetism is something to do with this, right? So what we're looking at now is a link between electricity and magnetism. That's okay? Real simple, right? So here's what we're going to look at now. Let's say I have a conductor. So I have a battery here. Right? You have your usual little switch. You have a little load. What's called this again? A fixed resistor, right? And I have a current carrying conductor here, right? If this current carrying conductor is not insulated, around it, there's a magnetic field. So around this current carrying means a current, right? What direction current is flowing again, Chinny? From where to where? The longest the what? 5.142. Yeah. Long is what? The long is the positive, short is the, and conventional flow is from. So current going this way, right? Oh, that's them next. Oh, right. So this current carrying conductor, current going down, has a magnetic field around it, right? So this current carrying conductor has a magnetic field. And the magnetic field around this conductor is in the form of little circles. We call it concentric circles. So around this, there are some circles, right? And the magnetic fields look something like that. So the one next marker. Anyway, just imagine around it, you have some little circles, right? These circles here are your magnetic fields. So what does that mean? Current carrying conductor has a magnetic field. But you'll notice there are no field lines here. So that will take us to our first rule. The right hand grip rule. Right? Imagine you're gripping something, right? And you're using your right hand. This is the first rule that we're going to learn. Your right hand grip rule. Right? Okay, a little draw here. Right? You mightn't be able to duplicate my thing, but right? So you have right. So you have your thumb and you have your 4 fingers. Each of them has a use, of course. Your thumb, right, gives you the current direction. And your fingers, in this rule, your fingers, that's all these here, your fingers give you the magnetic field direction. Magnetic field direction. So watch it here. Watch how it looks, right? Right hand rule, grip rule. Imagine if you're holding something and your thumb runs along it, right? So your thumb, direction current, and your fingers will point in the direction of the current. You okay with it? You okay with that? Sorry, magnetic field. So my current here is going where? Down. So my fingers point in the direction of the magnetic field. So they're going this way. You're seeing that? Right? I'm not too good at drawing 3D diagrams, so it's looking kind of hard to understand, right? So what they did is they, instead of you having to draw a 3D diagram, because remember, the wire is like this, and the circles around it like that. Right? So it's kind of hard to draw on the whiteboard. So what they did instead of the current going up and down, What they did is something like this. They do an X and a dot, right? What the X means? X means current going in. And the dot means current coming out of the whiteboard. And it's much easier for us to see the current, the magnetic field direction. So watch this. Current going in, right? So I'm taking my right hand, regardless if you're right hand finisher or left handed, you're always using your right hand, right? So your right hand, current going in, this finger current, so I have to turn it inwards. That's okay? So my fingers are pointing in what direction? Clockwise or anti-clockwise? Pointing in a clockwise direction. You're seeing that? So your fingers going in, so your thumb going in, and these fingers will point in a clockwise direction. You okay with that? Watch it again. Right hand, grip rule, thumb points inwards because this symbol means in. And your fingers point in a clockwise direction. You okay with that? So you see how it's much easier to see the field lines here than here, right? For those who could draw a good tree diagram, you could draw that from the right, right? But ideally, this is the way that we will learn it. So whenever current going in, clockwise. What do you think out will be? Anti-clockwise, right? Thumb pointing outwards, right? Thumb pointing outwards, fingers pointing in a anti-clockwise direction, right? You okay with that? So now we're going to learn what will happen when I bring this together with that. All right, in a little while. Copy down this. We have two more. Yeah. Again, two. Then join the diagram, going to have about faster, take up videos. Wow. Ito dulu lah. What do you call it? Who did it? Let me start with my masterpiece here. Current, come up. Right done. So that's your writing name, right? The right hand grip rule. I'll take it, pick over, right? Writing name underneath the right hand. There's the first rule you're learning, right? The right hand grip rule. You got about five, pick five. Well done.
So, yeah.
Well done.
Hi.
No, my girlfriend. So I come together, but yes,
Alright. 1 minute again, huh? Was a good song for you.
So what you doing just now? Please.
That's one.
There we go.
All right, nice. Everybody okay with that? So we're building up to see what will happen when I place this current carrying conductor inside here, right? Right, but before we do that, online, you all okay? Yeah, yes, right. So now here's what we're gonna do, right? We're gonna change that straight conductor into a slight coil. So watch this here. Piece of paper. Piece of paper, right? And through that paper, again, is a kind of little 3D thing, right? So through that paper, I am going to run a circuit through it. We have a supply, we have the usual thing here and a resistor, right? I am going to run a circuit through here. So current going which direction? Positive, negative, current going this way, right? Okay. So I am going to run the rest of the circuit through the paper here. Through the paper here and then coming back here. You okay with that? So just imagine this paper, right? The circuit just running through the paper. So current will come out here and current will go in here. That's okay? So now here's what we need, right? We need to figure out what the magnetic field will look like here and here. Right? What is happening here? And current coming out. Yeah? And when it's out? Anti-clockwise. Yeah? So therefore, around here, you will have anti-clockwise magnetic field. And here is automatically what? Here is, oh wait, there's not anti-clockwise. Anti-clockwise, right? And here will be clockwise. That's okay? So it's coming out here and going in here. Everybody clear with that? Yeah? Right. One thing that we have to figure out now is which of these is north and which of these is south. Right? Here's how you can remember it. Whenever you have something going clockwise, it's a south pole. So yes, looking. Yes, kind of clockwise. And now look at the anti-clockwise. If we write N looking like this. North. Right? So therefore, anti-clockwise, that's a north pole, here's a south pole. That's okay? So we created a simple little magnet here, north pole, south pole. So you might have a little interaction at the fields here, point how close they are. Yes, Samir? You okay with that? Right, Samir? So here's one coil. Samir, we're going to do some more coils. We're going to do 10 coils and see what we create. What would happen if you have like 10 coils in a circle? What is called that? Like a spring? We call it a solenoid. Okay? So head up flat. This one is a flat circular coil. Up on.
That's the on screen.
Up on. That's seen on screen.
You're right, it's just somebody.
All right. So yeah. All right, thanks. You did. So we're gonna leave it. That's flat circular. Right? Next one. Next one is a solenoid. So in questions like this, what they will ask you is to draw the magnetic fields around the flat circular coil and draw it past solenoid. Right? But I want you to understand what a solenoid is, right? Ready? Right. Look at here. Ready? So here's how a solenoid will look. You ready? So a solenoid looks like this. So it's a series of coils. All right? But it's important we understand how the current flowing on the coils. Otherwise, we'll get confused with the diagram.
I love you.
So watch this here. So we know here's plus and here's minus. Current going like this. That's okay, Soraya? Olia? So current going like this. So watch this here. In the coil, the current going in at the top and coming out at the bottom. In. You're seeing that? So it always going in at the top, and when it flows here, it coming out here. That's okay? So you have to pay attention to the way the coil is behaving, right? So it's going in at the top, and when you watch it properly, it's coming out here all the time. All the time. In, out. Same thing here. It's going in at the top there, and it's coming out here. You okay with that? So we have to draw the field lines that this solenoid will create. But again, this is a little hard to draw, right? So what we could do is we could simplify it. N is what? X. Out is dot. So I could draw the diagram. I could draw a diagram like this. That's okay? So I could draw a diagram like that instead. And here, we're going to use Fleming's right-hand rule by us at the different way. So you have to draw it again, huh? Fleming's, sorry, right-hand grip rule number 2. So right-hand grip rule number 1, current, magnetic field. That is only for a straight conductor. When I switch it to solenoid now, remember it's second version, right? That's okay? Using this rule twice. All right? Here's what you're doing now. Your fingers point in the direction of current, and your thumb points towards magnetic north. So listen again. Your fingers, 1, 2, 3, 4, right, points in the direction of the current, and your thumb points in the direction of the magnetic north. Ready? So watch it here. How the current behaving again? It's going in at the top and coming out. So watch my fingers. They're going in at the top. They're going in at the top and coming out at the bottom. Right? You're seeing that? It's going in at the top and coming out. So my thumb points towards what? The magnetic north, right? So if here is north, here is what? So, and how do field lines behave again? Field lines always leave the north and come into the south. That's all. I just want to draw the lines in between, right? So I'll leave it right here. Here's north and south. Right? Don't worry with inside here too much, right? You're not too concerned with what's going on inside here. Inside here, the little small dipoles is lined up on there. What you are interested in here is if here is north and here is south, magnetic field lines leave the north and go towards the south. You okay with that? Yeah? Sure? I'm going to over again, right? Right? So what is here? Right hand, what's his name? What's the name again? Right? So you have your right hand rule. Your right hand is used for what? Your right hand could be used for a straight conductor. That's using the first version. And the second version is using this one here. Magnetic north, current direction. Current going what? In at the top and out and bottom. So your fingers have to behave going in at the top, out and bottom. Right? And your thumb will automatically point towards the magnetic north. That's okay? So once you figure out where north is, south on the next side. Okay? Magnetic field lines leave the north and they come into the south. That's okay? Right? You could draw your field lines here too if you want, right? But I like that particular diagram. So I don't really want to draw it here. Right? But you'll figure out later on that here is north and here is south. That's okay? Follow the rule. No? Period? You don't understand this one? You understand? So you have the right hand rule, right? So the right hand rule, the right hand grip rule could be used twice. When it's for a straight conductor, current direction, magnetic field. When it's a solenoid, current direction, magnetic north. Right? So you're focusing on how these fingers point. Current goes in at the top, come out at the bottom. Yeah, you see now there, in here, out. So therefore your fingers have to behave like that. Go into the whiteboard and come out. And your thumb will tell you where is the north. All the time. Right? So if it's the other way around, then the north will be on the opposite side. So this thumb will tell you where the north is. So it goes in here, comes out. This thumb will point to where the north is. Here's north. That's okay? Sure? Anybody else confused? So it's one rule we use and put two things. Right? All the others are one, we put one thing after that. Right? So those who can envision it, right? There's a solenoid here, right? And at one particular point in time, right? at one particular point in time, current on the top, the current coming, going in, and then it coming back out and bottom here. So a solenoid would look like this. But we take a 3D diagram and convert it to a 2D diagram. So we take this 3D, right? And we convert. Right. We convert this 3D spring into a 2D. And to simplify it further, I said, you know what? Instead of drawing this, we recognize current always going in and top. Right? And we know that current going in carries this symbol. So I draw X's on top. And underneath, current coming out. So I draw a circle on top. So this here, without the field lines, is a solenoid. This here is that. That makes sense? You sure? Right? All I didn't do is I could have put more if I wanted, right? But these symbols represent the little coil of current going in. And these symbols represent the part where the current is coming up. Understand that? You sure? And then I applied right-hand grip rule. I applied the right-hand grip rule to figure out the magnetic field. Yeah. To figure out these directions here. Yeah, just put it back.
Because that's they're two different numbers. That's almost done, so that's almost done.
Okay, we're not. No. This one is the hardest to see. The rest is. This one is the hardest to see here. Right? Huh? We have two more to join. Everybody easy. I'm gonna take that and put it in a magnetic field now. Anybody confused?
Leave it. They're going. How is that trip? Go leave it.
Good. Like my new slippers. So what you must put that on? It's possible you can buy my clothes or something. I know, it's so black and
Right? Any questions? Access, no, this is something tricky. Alia. You sure? Anybody else? Emily, you follow that?
That's not my.
You sure?
Yes.
Right. I'm gonna just make sure, yeah? I'm gonna ask some people online too.
So,
What do you put there? What do you put there?
he's in the-
But I thought that all this is go and log in there.
This, what is that?
I found baffles. This is like, we already have a baffle.
Right. Here we have a solenoid again. Right?
Yes.
Here we have a solenoid again, right? So I want you to use the right hand grip rule and draw the free lines around here for me. Hurry up, Aaron, hurry up. Everybody is online. So that's my fault, bro. Hurry up, try that here. So I want you to use the ruler, go ahead, do it here. I want to see you use the rule. People like Emily and Jenny, I want to see how they use the rule. Okay, coming forward.
Whoa, whoa, whoa. Whoa, whoa, whoa.
All right, online, I want you to message on which side, left or right, will have a North Pole. All right, online, message which side, the left side or the right side will have the North Pole.
Dots. What was that? Oh, I like. Right.
Again, I want to see you use the rule, right? Online, stand in the left or right?
Circle.
Yeah, coming forward.
Está police. Which police? Polentan.
Draw the free lines.
Está Polentan.
Right, online, check back and see which side is north and which side is south, right? Left and right. Sorry, I just want to know which part is north. Okay, one now. Why put one? Sorry, maybe
I didn't have it. Am I fixing?
yes, do it properly. But sorry, I will. Right, remember magnetic fields leave the north and go towards the south.
Why is it going like that? Put the leave north. So why is it going this way? Put it going north to south. Put it going north to south.
So the arrows on top. Right, most of you all had it. Most of you all had it, right? Right, so just pass on to taking the rule, right? Right, watch here. So that means what? That means out, X means so the magnetic field behaving like that. Okay? Current behaving like that, so north is down there, north is here, south is here. Magnetic field lines leave the north and come into the south, right? They leave the north and come into the south. Here's south, right? Actually, I should write it here. So I will know that inside here is north and south, right? And then, although you have your circle, yes, some of you all have this circle, but you forget to put the arrow. Right? Leave the north going towards the south. Don't worry what's inside here. Right? I'm putting no arrow here. So I don't want to confuse you. Outside is what we're interested in. All right? Yeah? All okay? All okay? All sure, right? All right. Now for the real thing. Here's what we're gonna do now. Now we're gonna take current carrying conductor and put it in a magnetic field. Next heading. Current carrying conductor inside a magnetic field. Current carrying conductor inside a magnetic field. Current carrying conductor in a magnetic.
Right. My head was
All right, let's go again. Right, so, right, any questions online there? All right, good job online. Some was again wrong. Right? But you just follow now those who got it wrong. There's that.
What?
Right. So now for the last rule for today. Last one. Right. So here's what we said. We said that if we put magnets together, like a north and a south, right? We should experience a force. Are you okay with that, Pishish? We should experience a force, right? If we put a south and a south together, they will be pushed away, right? That's okay? So whenever two magnetic fields interact, they experience a force. Nice. So here's what we're going to do now. We are going to take a current carrying conductor. That symbol means current carrying conductor. Right? We are going to take a current carrying conductor and put it in between a magnet. Right? And the magnet has a magnetic field. The magnet has a magnetic field. And this current carrying conductor has a magnetic field. So they both have a magnetic field. So we should experience a what we see. We should experience a force. Okay? So therefore, if these two can't move, this will experience a force. And the rule that we're going to use is Fleming's left-hand rule. And today, you will come on the board for this one. Let me show you understand this one. Right? So what you see? Why this thing? I find in the middle here.
So the screen is fucked up. Come on the board.
Right. Somebody shift that.
What kind of answer?
Right. So then again, they physics gang, they design it. Right. All ready? So how do we use this rule? This rule, for those that kind of fingers and things, yeah, they try to straighten their finger. Right? That's how the rule works. Thumb, 90 degrees to thumb, first finger. Then the middle finger is 90 degrees to both of them. That's all right? Right? Middle finger now, 90 degrees. No. Don't do this, please. I'm starting over. 1, 2, 3. Make sure these two 90. Right. Push that one out some more. Right. That's okay? Right. All here. This rule becomes difficult if you can't keep your fingers like this. Right? You have to stay like this all the time. Okay, so what you do is move your position or your notebook or your wrist. You don't move these three things. You have to stay like this all the time. Otherwise, you will get confused. Your rule must never look like this. Okay? Your rule must never look like that. It must look like this. Okay. So, what does this thing mean? Right, let me give you a little diagram. Thumb, first finger, middle finger. Right? We don't need these two, right? Just need these three. Your thumb is the direction of the force. Right? Your first finger is the direction of the magnetic field.
And that's fine. But that's not supposed to be done. That is CSEC. No. I forgot to put it down. So you didn't put that thing on.
Well, it's out. Just pretend it's out now.
It's out. So fix it.
Right? Everybody okay with that? So watch this here. Watch it again. So for your left-hand rule, thumb represents the direction of the force. First finger, Vishish. Come, Vishish, sleepy. Come now. Your first finger, direction of the magnetic field, and your middle finger, direction of the current. All right? Are you okay with that? Ready? So watch this here. The purpose of the rule, just like the right hand grip rule, the purpose of the rule is to find this. How is this finger behaving? Everybody okay with that? Right, come Ginny. I'll do this demo on Ginny. My husband, yeah. Right, online, so I'm going to show you how to use the rule, right? Left hand. Remember, the name of the rule is the Fleming's. I'll give you a note just now. Left hand rule. So you must use your left hand, right? So watch this here. Left hand. Do this. Right. Everybody okay? Force, magnetic field, current. So let's start with magnetic field. Magnetic field move from where to where?
North to south.
North to south. And this current is where? In or out?
In.
Out, right? So let's go. Right? So she started with trying to figure out the magnetic field. So the magnetic field is north to south, so it's pointing downwards. That's okay? This finger pointing downwards, right? But the middle finger pointing in. Did it supposed to point what?
Out.
Out. So come around. Right. So watch this here. Watch it here, right? So magnetic field north to south, and the currents going inwards. You'll see that? Try to move around a little bit, right? But current going in, magnetic field going north to south, and the force is in one direction. That way. You're seeing that?
Yeah.
Everybody seeing that? We have plenty more to do, but I wanted to understand the concept, right? So the magnetic field north to south, right? This current is out. What she get us now? That way, right? This way. What we just do wrong then? All right, so I do it over here. Did I do something wrong there? Did I do something wrong there? I use the left hand, right? All right, but we'll do it back again. So watch this here. Magnetic field, current, force. Right? Magnetic field going north to south. Current coming out. So my thumb points in direction of the force. So the force is here. Are you okay with that? Yeah? Everybody okay with that? Watch the next one to make sure you catch it. No? Well, it's one. It's one good. What yours done?
That's my marker.
Well,
That's my marker.
I had a mark like that there. Yeah, well, you lost it. Ready? Let's go again. So, Chine, what are the yours? What direction was it? This way? Or this way? What we did wrong? It don't matter. Anyway, let's go again. Magnetic field, current, force. Okay? So X means what? X means in. Check it back, right? X means in. Dot means
Out.
out. So let's go. Magnetic field going where? North to south, so it's going upwards. That's okay? And X means what? X means in. So I'm gonna make this middle finger point inwards.
Right, okay.
That's okay? So therefore the force is towards me. Yeah? Arya? Anybody confused? Anybody confused? Yeah, Taisha? Right, watch it again. Watch it again. So magnetic field, current, force. Magnetic field going north to south. So my first finger going upwards. Right? Current going where? Current going in. So I'm going to make this finger point inwards. Right? Y'all seeing that? So remember, you have to do it relative to how you write it on your paper. All right? So draw it on your paper and do the same things I'm doing. So magnetic field going north to south, current going in. So therefore the force is to the right. You okay with that? Yeah? Copy it down. We have plenty more to try.
You know how much you can do? What's
All right, copy it down. Try number 3 and 4. I'll give you the note after. I'll give you a note, but I'll give you the note. Who confused? Somehow what's up? Online, are they okay? We have 2 more here. I wanted to try it. Right? So for number 3, message left or right. Number 4, message up or down. Who confused? I'll show you again.
Right, yeah. And then yeah, but see. Soraya.
I have to have the higher goal. What direction does magnetic field flow in?
What?
North to south, right?
Yeah. Hey, stop it. Put your hand down. Put it down. Right, right. Go like that. What you think, right? If I can fix it. I'll wait. My back. It's my back. It's my back.
Right, I'm gonna show you them now, right? So, right, so I saw a mistake where some people put your magnetic field going north to south to north, right? Magnetic fields go from north to south. That's okay? So watch here, right? Magnetic fields going north to south. So I take in, remember, everything has to happen based on what you drew in your book. So if this is your white page here, right, you're doing everything on it, north to south. So I'm taking my finger, my magnetic field, and I'm laying it north to south. That's okay? You're okay with that? Now X is what? X is in. But my middle finger pointed out. So I have to get my middle finger pointed in and my first finger still pointing down. So I achieved it there. Y'all seeing that? My middle finger pointing towards the whiteboard or your page, and your field going down, and the force pointing towards me.
Yeah, I get out.
Everybody okay with that? Next. Hold on, come on. Right? Watch here. North to south. Magnetic field, north to south. That means what?
Oh.
So my first finger pointing north to south, and my middle finger pointed out. So my thumb points towards the upward. Right? Why does that happen now? Everybody clear with the rule?
Yeah.
Right? Don't forget it for next week. Right? Wait, being done, don't pass up. Why does that happen? Why it is the conductor return going upward? Why that happening? It must have a reason why the conductor being pushed upwards, the conductor being pushed to the right, the conductor being pushed to the left. Say that. Yeah, you were saying something. Huh? Anybody? Wanna guess?
The question.
What causing this conductor to be pushed upwards? Something to do with that. Any guess? Huh? Yeah, a force, but something creating the force. Gravity, no, gravity will push it down. Not gravity. Anybody online? No guess? Yes, a magnetic force created by not what picture is it? By the magnetic fields.
I say that, sir.
Huh?
I say that.
You always say that after.
I say that.
Watch. So watch what happening, right? What happening here is that remember these two have magnetic fields. So they're building up here. And they have a few here. So if you have more field lines underneath and less on top, what will happen? Push it upwards. That's okay? Same thing here. It's going this way because there's a buildup of field lines here. There's a buildup of field lines here. So there's more here and there's less here. So what will happen? It will push it this way. That's okay? So on the opposite side has more, pushing it towards, well, where the force is. That's okay with that? So imagine you have a rubber band and you build up the pressure on the rubber band here and you release it. What will happen? It'll move this way, right? That okay with that? All right. We didn't get a note for centimeters.
Time to go home. 5 minutes.
Right? Just make a note of this. Fleming's left-hand rule. I'll give you the note next week. Fleming's left-hand rule. I'll give it. In fact, your homework is to write what happened in there. Write your rule on what's going on there. All right, online. So we did Fleming's left-hand rule. Next class we're going into the motto. Okay? Motto.
Do we draw this?
Yeah. Join the field line, please.
Sam, do you hear me?
Join the field line, right? All right, online. So, for homework, I want you to write a small note, right? On Fleming's left-hand rule.